Okay, so now we'll start this module on stack ADT. So again, from an ADT point of view, what are the logical features you would expect from a stack? Now a stack is kind of like um, last in first out based ADT, in the sense that, so if you have say a pile of books, you keep piling one book on the top of the other. So then if you want to remove a book from the pile or the stack, the first book that we will pull out of the stack is the last book that you put on the top of the stack. So that is why we say a stack will operate in a last in first out fashion. So for example, now if you keep pushing integers, so 0, then you push 1, 2, 3, 4, 5 to the stack, then what comes out of the stack is 5, not 0. The first thing that come out of the stack is what is in the top of the stack. So you notice right away some terminologies that we use. So to add things to the stack, we say it's called the push operation. So we push to the stack. To remove something from the stack, it's called the pop operation, and we do both push and pop to what is already in the top of the stack. So when you want to push 5, we push 5 on the top of 4. So before pushing 5, 4 is in the top of the stack. So then you push 5, then 5 becomes the top of the stack. Now when you pop from the stack, what comes out is again what is in the top of the stack. Okay. Now in addition to push and pop, we can also do what is called a peek operation on a stack. So peek operation is just like looking into the top of the stack and seeing what is in the top of the stack, and it's like a read operation. So you're not removing, you're not popping out of the stack. Now we can also check if the stack is empty. So if the stack is empty, that means there's nothing in the top of the stack. Okay. Now we would like to implement all these 4 operations of a stack in big O of one time or constant time. Okay, so now again, this is an ADT point of view. What are the logical features you would expect from a stack? Now from the implementation point of view, and that is where the data structures come, you could implement a stack as a dynamic array or a single linked list or a double linked list. So let us now start with the dynamic array based implementation of a stack. Now we use the same kind of member variables in the stack class, which is implemented as a dynamic array. So you have a pointer to an array of integers, so that's going to kind of point to a block of memory where you're going to store the integers and represent them as a stack. And then max size of the array, so what's the maximum number of elements the array can have, and then the top of the stack, so this is going to be same as the end of array variable. So remember in the list implementation, we're using a dynamic array, we use the end of array variable to keep track of what's the index of the last element that we inserted to the or the end of the array. So similarly, the top of the stack, like in this example I show here, so this is an array of 7 integers. It can store 7 integers. That's max size is 7, and index will range from 0 to 6. So the way we would have pushed things to this array is, or the stack is, pushed 10 first, then added push 7, then 5, then 9. So 9 is the last element that we push to the stack, and that is the top of the stack, which is at index 3. So if I now push one more element, it will go to index 4, and that will become the top of the stack. Okay, like this. Now the constructor for the stack will take up the size of the array that you want to set up. So once you get the size, you can say array equals new int size. So the base address of the array will be stored in this array pointer, and max size will be equal to the size. And then initially we have just set up the array, we have not yet filled the elements, so the top of the stack will be -1. Okay. Now you can check if the stack is empty by checking if what is the value of top of the stack. So if the top of the stack is -1, that means the stack is empty, otherwise it is not empty. Okay. Now you can also resize the stack, like means you can double the size of the stack. So it's very similar to what we did for the list. So you copy the, you create a new block of memory that is double the size, and then copy the content of the previous array to this new array, and so on. Now, so when we need to resize, if you want to push something to a stack, so this is push operation in the case of a stack, the dynamic array is going to be same as inserting at the end of the array. So the first thing you would check is if the top of the stack is max size minus 1. So for example, if we have all the 7 elements fill up in the stack, then top of the stack will be 6 and max size is 7. So top of the stack will be equal to max size minus 1. And if that is the case, then we need to resize the array. Means we need to double the content of the array. So you say pass 2 times max size is the argument, and that will double the content of the array, and then this is the resize code. We'll copy the content of the array from the previous block to the new block, and so the array pointer will really point to that new block of memory. So once we do the resize operation, we can push the element that you want to add to the top of the stack. So here I do array of plus plus top of the stack equals data. So this is called the pre-increment operation. So top of the stack will be first incremented by 1, and then you access the array at that index, and then you set the value of that index to be the data. Okay. Right. So let me stop. 1 second. Okay, so now you can also do the speak operation on the stack. So this is like looking into the top of the stack and finding what is there. So if the top of the stack is not -1, that means it's greater than or equal to 0, then you can return what is in the top of the stack at that index. Else return negative, some invalid value indicating the stack is empty. So when you do a peek operation on an empty stack, you need to indicate to the user that there's nothing to look at the top of the stack by returning a negative value or some large invalid value to indicate that the stack is empty. Now you can do a pop operation on the stack. So pop is different from peek in the sense that you are removing something from the top of the stack. So if the top of the stack is greater than or equal to 0, then you can return array of top of stack minus minus. That means your first, this is called post decrement operation. So you first make use of the current value of top of the stack and return that data at that index at the array of top of the stack, and then do a minus minus. So that means you're decrementing the top of the stack after you access the element at top of the stack. Now if top of stack is less than 0, that means the array at the stack is empty, so you can return again the invalid junk value to indicate that this user that the stack is empty. Okay. So in terms of the cost of the implementations, now for the push operation with the dynamic array, we would take big O of n time because of the resizing necessity that will come up whenever you want to resize the array. So at the worst case, you have to do n copy operations, so that's why it's big O of n. The pop can be done in constant time. All you have to do is just check if the top of the stack is equal to 0 and then return the element at that index. Similarly, the peek can be done in constant time. Now with the linked list, both single and double linked list, we could achieve all the 3 operations in constant time. But how you do that is important, because in a single linked list especially, insertion and deletion has to be done at the beginning of the list. That means the node next to the head node should be considered as the top of the stack if you want to accomplish this in constant time. A double linked list, we could do it either near the head node or near the tail node, and we'll do near the tail node. Okay, so this is just something for you to think about before we start the next video. So let me finish this video.